Hey guys, today we're going to look at section 1.5, polynomial functions and complex zeros. Our learning target is I can identify key characteristics of polynomials. So today we're going to look at complex zeros of polynomials. And as a reminder, complex refers to both real numbers and imaginary numbers or non-real. And remember, if it's imaginary, it has to have I in it for the imaginary unit. So zeros, which are the same thing as x-intercepts, roots, solutions, and linear factors. So if we have p of a equal to 0, so some polynomial set equal to 0, then at a, or x equals a, that will be a 0 or a root of p. Which, remember, a 0 is the same thing as an x-intercept. And we will have an x-intercept at the point a, 0. And as long as a is a real number, then x minus a is a factor of our polynomial. So as an example, if we have f of x equals x squared plus 4x plus 3, we can factor f of x into x plus 3 and x plus 1. And in order to solve that, remember we want to set both factors equal to 0, so x plus 3 equals 0, or x plus 1 equals 0. And if we subtract 3 on both sides, we get x equals negative 3. If we subtract 1 on both sides, we get x equals negative 1. So that would mean f of negative 3 equals 0 and f of negative 1 equals 0. And that means we would have a 0 at negative 3, if we just use that 1 as an example. And we would have an x-intercept at negative 3, 0. And then we would use our factor x plus 3. And then if you recall from Algebra 2, we can have repeated zeros, which means zeros have multiplicity. And so if our factor is repeated n times, then the corresponding 0 of the polynomial has a multiplicity of n. And so remember, we look at our exponent once our polynomial is completely factored, and that is where our n, or our multiplicity, is found. And usually we know that polynomials pass through the zeros on the graph, especially with linear functions. However, when we have zeros with multiplicities greater than 1, the graph behaves differently at that 0. So for example, we have our function y equals negative 0.01 times x plus 4 times x plus 1 to the third power times x minus 3 to the second power. So we have an understood exponent of 1 on our first factor. We have a cube on our second factor, square on the second, which means y's degree, if we add all of those together, y's degree is 6. However, our different zeros have different multiplicities. So when we want to determine the multiplicity of the 0, it is the degree of that factor. So x equals -4 only has a multiplicity of 1, and we can see at -4, it crosses the graph. And at x equals -1, we have a multiplicity of 3. And when we have a multiplicity of 3, our graph creates a little curve, kind of like a cubic function. Or kind of like an S. And then at x equals 3, we have a multiplicity of 2. And we can see on our graph on the right, it just bounces off the x-axis at 3. And you can see below that the graph of the polynomial is tangent to the x-axis at x equals 3. And that happens when we have any even multiplicity. So when your multiplicity is even, you just touch the x-axis. And when your multiplicity is odd, you will always cross the x-axis. So we have a couple of examples below, and for each one, we're going to determine the degree, find all the zeros, state their multiplicity, and then sketch a general graph. So first, we have f of x, and if we look at that function, it is already completely factored, so we do not have to do any work to find our zeros. And f of x, its degree, if we look at all of our exponents, so we have 3 plus 1 plus 2 is a degree of 6. And then if we want to determine our zeros, so our first 0 comes from x cubed, and that would give us a 0 of x equals 0 with a multiplicity of 3. Our next 0 would be at x equals -1 with a multiplicity of 1. And our last 0 would be at x equals 4 with a multiplicity of 2. So if we want to sketch our general graph going from -1 up to 4, we know at -1 we are going to cross. At 0 we're also going to cross. It's just going to be a little bit of an S curve. And at 4 we're going to bounce off. And then if we think about, so our degree of f of x is even, which means both of our ends are going to go the same direction. And because our leading coefficient is negative, we know that both ends are going to go down. So when we cross through -1, we're going to come from the bottom of our graph, and then we kind of curve through 0, and then we got to go back to 4 and just touch and come back down. And that's generally what f of x would look like. Next, if we take a look at g of x, we do have to do a little bit of work here. It's not completely factored. If we look at this x squared minus 4, that is a difference of squares. So we can factor that into x plus 2 and x minus 2, which means g of x will become 3 times x plus 2 times x minus 2 to the 5th power, because we have 4 here and 1 more up here. And that tells us that the degree of g of x is 6. And if we think about our leading coefficient here, it's positive, so unlike f of x, both ends are going to go up. Then looking at our zeros, we only have 2 of them. Our first one will be at -2, and it has a multiplicity of 1. And our last 0 is going to be at 2 with a multiplicity of 5. So at 1, it'll just cross right through, or sorry, at -2, it'll cross right through, and at 2, it'll cross, but it'll also do a little curve. So if we want to sketch out our general graph, we got to go from -2 to 2, and we know both of our ends are going to go up. So if we just cross right through -2, and then we're going to curve a little bit when we cross through +2. And that could be roughly the shape of g of x. Lastly, we have y, which we do have to factor quite a bit. So first, we can take a greatest common factor out of our first set of parentheses of x, which leaves us with x squared minus x minus 6. And then we can factor that inside set of parentheses again to be x minus 3 and x plus 2. And then our last set of parentheses here, we can factor to x minus 3 and x minus 4. Which means our function y, we do not have anything outside of our original sets of parentheses. So we'll just have our x in front, and then we have x plus 2, x minus 4, and x minus 3. We have 2 of those, so we're going to square that factor. And the degree of y is 5. And because that is an odd degree, that means our ends of our function are going to go in different directions. And because our leading coefficient is an understood 1, that means the left side will go down and the right side will go up. So next we'll determine all of our zeros. Our first 0 will be at 0. With a multiplicity of 1. And we have quite a few zeros with a multiplicity of 1, so we'll list them all together. We have 0, -2, and 4. And then our last 0 is at x equals 3, and that has a multiplicity of 2. So let's sketch our graph. going from -2 to 4. So at 0, -2, and 4, we're going to cross through it. And at 3, we're going to bounce right off. And remember, we're going to start by increasing to -2, and then decrease to 0. We're going to increase to 3, bounce off, and then we go up through 4. And that would be the general shape of y. So to recap, you need to completely factor your function in order to identify your zeros, and then you look at the degree of the entire function in combination with its leading coefficient to determine how the ends behave, and that will help you sketch the behavior of the middle of the graph at your zeros. So now let's look at when we have complex roots. So when we have complex roots, that means our roots have an imaginary number, which contains the imaginary unit. And this means you will not see those on the graph, kind of like the graph to the right does not cross through the x-axis. And that is x squared plus 1. And if we set that equal to 0 and solve, we can see that our zeros are plus and minus I. And if you recall, all imaginary roots come in pairs. So if you have a plus bi as a root, then you must have a minus bi as well. And we call those conjugate pairs. So for the examples below, we're going to determine all of their conjugate pairs. So for A, we have positive 4i, so its conjugate pair would be negative 4i. And then I want you guys to try B. For part C, we have 2 minus 3i, so we want to change the sign of that imaginary part, which gives us the conjugate pair of 2 plus 3i. I want you guys to try part D as well. So the fundamental theorem of algebra states that a polynomial of degree n has to have exactly n complex zeros when you are counting multiplicity, and that includes real and imaginary. So just to simplify that, your degree is going to be the same as the number of complex zeros. So for example, if we have the graph of f of x, we know that x equals I square roots of 3 is a 0 of f. And if f has degree of n, what is the least possible value of n? So essentially this is asking us to find all of the zeros from the graph and the given complex zero and determine what the least possible degree of f of x could be. So if we look at our graph, we can see that we have a 0 at -1, which has to have a multiplicity of 2, or an even multiplicity, because it bounces off. And then we have another 0 on our graph at 3, which appears to have a multiplicity of 1. And then we are also told that x equals I square roots of 3 is a 0. And because our complex roots have to come in pairs, we also know that negative I square roots of 3 must be a 0 as well. So if we think about those 4 zeros with their multiplicity, so remember, negative 1 has to have a multiplicity of 2, 4, 6, so on and so forth. And remember, we're looking for the least possible value of n. So we only really want to look at 2 having, or negative 1 having a multiplicity of 2. So when we count all of those up, f has to have a degree of 5 or more. So now we're going to look at how to determine the degree from a table of values. And we can only do this if we are looking at equal width input intervals, which means the change in x must be constant. So your delta x must be constant. And if we look at our table below, we can see that it is. Each change in x, we are only adding 3. So as long as we have those equal width input intervals, we can determine the degree of a polynomial by looking at or examining successive differences in the output values, or looking at how y is changing. And the number of successive differences we need to look at in order for those differences to be constant tells us the degree of the polynomial. So if we look at g of x, our first difference, we're adding 2, and then 10, then 17, and then 23. So since the first difference, this is the first difference, because that is not constant, that tells us that g of x is not linear. So then we want to look at the second difference. So from 2 to 10, we would be adding 8. From 10 to 7, we would be adding 7. And from 7 to 23, we would be adding 6. So because the second difference is not constant, it is not quadratic. So remember, we want to keep looking at the differences until we find it to be the same. So now we're going to look at the third differences. And if we think about going from 8 to 7, we would be subtracting 1. From 7 to 6, we would also be subtracting 1. So because our third difference is constant, that tells us that g of x is cubic. So our degree is 3, since the third differences are constant. Next, we're going to look at even and odd functions. So if you recall, an even function is symmetric over the y-axis, which means it has reflectional symmetry, so it reflects over the y-axis here. And algebraically, we know it's an even function if f of negative x is the same as f of x. And you can see an example below. F of x here is an even function. An odd function is symmetric about the origin. Remember, the origin is 0, 0. And when we are symmetric about the origin, that is rotational symmetry, so it rotates. And when it is an odd function, g of negative x is the opposite of g of x, or the opposite of your original function. So looking at example 5, we are going to determine if these two functions are even, odd, or neither algebraically. So h of x, we want to think about h of negative x. So anywhere we see an x, we want to substitute in negative x. And then if we think about simplifying that down, because our exponents are even, anything raised to an even power is positive. So we're going to have 2x to the 4th power minus x squared plus 5. And because that is the same as h of x, that means that h of x is even. Another way to look at it if you think about h of 1 compared to h of negative 1, that is another way to think about when your function is even versus odd. So if we think about h of negative 1, we would have 2 minus 1 plus 5. So h of negative 1 is 6. And we also want to find h of positive 1. And if they're the same, we know we have an even function. So with h of 1, we have 2 minus 1 plus 5, which is also 6. So because h of negative 1 and h of 1 are the same, that also tells us that it's even. So now let's take a look at k of x and determine if k of x is even or odd algebraically. So we're going to substitute in negative x and see what we get. So we have negative x cubed plus 3 times negative x minus 1. And when we simplify that, anything to an odd power or a negative number to an odd power will stay negative. So we have negative x cubed. 3 times negative x would give us negative 3x, and then minus 1. And because not all of our signs change, that means that k of x is neither even nor odd. Lastly, we're going to look at polynomial inequalities. So when we write f of x, remember we are referring to the y values on the graph. And if we talk about f of x being greater than 0, that means the graph is above the x-axis. And if f of x is less than 0, that means the graph is below the x-axis, where all of our negative y values are. So looking at the graph above, first it asks where f of x equals 0, and we have zeros at x equals negative 3, negative 1, and positive 3. Next, it's asking us where f of x is positive. So we want to look above the x-axis. So we're first positive from negative 3 to negative 1. And then we are also positive from 3 to infinity. And we're using open intervals because we're looking at strictly greater than 0. C is asking where f of x is less than or equal to 0, so we will have closed intervals. And we are less than or equal to 0 from negative infinity to negative 3. And also from negative 1 to 3. So when we are trying to determine algebraically where polynomials are positive or negative, we first want to solve f of x equals 0 and find our zeros. Then we create what is called a sign chart with our solutions from step 1. And we want to test values within the intervals to see if the interval is positive or negative. And then we interpret our sign chart to answer the problem. So, for example, we have our first polynomial, which already is factored for us. So we can see we have zeros at 3, negative 1, and negative 4. So when we create our sign chart, we want to look at those 3 values. And we want to think about what's happening between them. So if we first look at what's happening at, say, negative 5, Well, negative 5 minus 3 would be negative 8. Negative 5 plus 1 would be negative 4. Negative 5 plus 4 would be negative 1, which would, if we do a negative times a negative times a negative, that would end up being negative on that first interval. And then if we think about between negative 4 and negative 1, we can test negative 2. And negative 2 minus 3 would be negative 5. Negative 2 plus 1 would be negative 1. Negative 2 plus 4 would be positive 2. So we would have a negative times a positive, which would end up getting us a positive. So from negative 4 to negative 1, we are positive. And then we want to test the rest of our intervals as well. So our next interval contains 0. So 0 minus 3 would be negative 3. 0 plus 1 would be 1. 0 plus 4 would be 4. So a negative times a positive would get us a negative number. And then our last interval, we can check 4. So 4 minus 3 would be 1. 4 plus 1 would be 5. 4 plus 4 would be 8. So positive times positive means our last interval there would be positive. So we know our function is greater than 0 from negative 4 to negative 1 and from 3 to infinity. And remember, we were using open intervals because it is strictly greater than 0. So I want you guys to try example 7.